right? So do we believe, how accurate do you think this is? Remember, we had done a lot of approximations, right? We assumed a class of boundary layer profiles, we had a fitting and things like that. So would you expect this to be about like 10% off, 50% off, 20% off? Take a guess. 25? Okay. Anybody else? Take 5? All right. So you have a lot of faith.
10.
Okay. Lee? 10. Okay. And okay, 50. Wow. Okay. Let's see. So let's actually compute the same thing using something we coded up in the thin layer. Let's actually solve the full thin layer approximation, right? Okay. So remember, not the FS, but the thin layer code. Where is it? Okay, so this is what we coded up last time, solving the full thin layer equation, right? We are advancing in C, and every time we are solving the thin layer equation to get the full boundary layer profile. Okay. So after this, we can compute theta, right? So basically, I will just take this code, which is not actually very useful. Put it here. So this code computes the displacement thickness, and instead let's compute the momentum thickness. We just redefine d as the velocity times 1 minus velocity, right? And theta is equal to the sum, but that's in the eta coordinate. So let's actually translate it into the real physical coordinates by multiplying by what? So let's see. Let's go back to, I think we have to go back to the thin layer equations, and when we are transforming, yeah, we are the delta we used to non-dimensionalize the y coordinate, it's square root of nu times c divided by ue, right? So square root of nu. Actually, in this equation, we didn't have any sense of nu because it's already non-dimensionalized. So let's keep it consistent. 10 to the minus 5 is what we used in Thwaites, I think. Right, okay. Times what? Times c. So c is already a variable. Divide by ue. Ue is this guy right here. Okay, so let's putting this ue. So that's my theta. Okay. Sorry?
How should you do dot divide?
Dot divide. Oh yeah, this c is a. I can do dot divide. This c is a. It's a scalar. It's not a vector, so it's fine either way. Yeah. Okay, and let's make thetas. And thetas is equal to theta. I think I'll have a divide by 0 when c is equal to 0, right? So I need to do if c is equal to 0, theta is equal to theta times square root of 10 to the minus 5. Basically, when c is equal to 0, c divided by, I mean, if you do a Taylor series analysis, it'll be just 1. All right. So square root of that. Else, I'll do this full thing. Okay. And at the end, let me make a figure and plot. I don't think I have c here, so I'll plot the full 0 to dc to 10. And thetas. So let's define the grid. Actually, let's just run the whole thing. It's solving. It of course takes much longer than the Thwaites method, which takes no time. So we get roughly the same curve, right? So this is the family of boundary layer profiles. This is the thetas. And why don't we plot on top of each other? Where is this? Thwaites method. Let's just hold on and plot. Oops, plot is red. Let's say red is Thwaites method, and we had this blue. It's just figure 2 to make sure we are on the same plot. Change folder, right? So it's pretty good, right? So we have this red on top of blue. I mean, if you zoom in, you can see they're actually two different lines. But the accuracy of Thwaites method is pretty good if you have a smoothly changing external velocity profile.